How Newton might interpret gravity was sufficient to permit us to fly from the Earth to the Moon. At any point, one might wind up lost in the ticking hands of time, contemplating whether our understanding of it is only the tip of the transient iceberg. On its head, his discovery isn't merely a hypothesis. It's a key that could open the doors to the mysteries of the universe, uncovering a cosmos more intricate and inspiring than we ever dared to imagine. How does Brian Cox's new hypothesis challenge our traditional understanding of time? And what are the possible ramifications for our perception of reality? Join us on a fascinating exploration through the chronicles of time itself as we delve into Brian Cox's recently unveiled groundbreaking theory on the nature of time in the vast universe around us. Secrets are waiting to be uncovered, and some of these mysteries involve perplexing concepts like time and gravity, which are fundamental components of our reality. Imagine a reality where time behaves strangely. It can either slow down or speed up. Furthermore, the force that keeps us grounded might not be what it seems. This is the realm of Albert Einstein's theories of relativity, where our understanding of time and gravity takes an unexpected turn. Albert Einstein, a renowned figure, offered us a new perspective on the universe through his theories of relativity. His work laid the foundation for understanding how time behaves under different circumstances, especially when traveling at extremely high speeds. Everything began in the early 20th century when Einstein proposed two revolutionary theories: the special theory of relativity and the general theory of relativity. The special theory of relativity, published in 1905, transformed our understanding of space and time. In simple terms, it tells us that the laws of physics remain the same for all observers who are not accelerating, regardless of their motion. This theory introduces the concept of relativistic effects, including the famous idea that time can stretch or slow down under certain conditions. One fascinating thought experiment used to explain time dilation is the light clock. Imagine being inside a spaceship moving incredibly fast, almost at the speed of light. Inside the spaceship, a beam of light bounces between two mirrors, perpendicular to the direction of motion. According to the laws of physics, the speed of light is constant for all observers, so the light beam must appear to travel along a longer diagonal path. The time it takes for the light beam to complete its journey should be the same for both the observer inside the spaceship and the one outside. However, since the path is longer for the external observer, it seems like it would take more time for the light to finish its journey. This apparent time difference between the two observers is what Einstein called time dilation. Time slows down for the observer moving relative to the stationary onlooker. In this scenario, time behaves differently depending on your motion. Understanding how things change when they move fast, known as relativistic effects, isn't just theoretical. Scientists use massive machines called particle accelerators like the Large Hadron Collider to make particles move extremely fast, nearly at the speed of light. When things move this fast, we must account for time in a special way to make accurate predictions and measurements. Albert Einstein developed the special theory of relativity in 1905, and it changed how we perceive the universe, especially regarding time and motion. This theory challenges our intuitive understanding. It states that the standard rules of physics are the same for everyone, even if they are not moving. This differs from our everyday experience, where we might think that if something is already moving and we add more speed, it gets faster. But Einstein's theory says there is a maximum speed. Nothing can go faster than the speed of light. In this perspective, events that seem simultaneous to us might not appear the same way to people moving close to the speed of light. Another concept from this theory is length contraction, meaning that if something is moving, it looks shorter in the direction it's moving when observed from a stationary position. Then there's the famous equation, E equals mc squared, which shows how energy and mass can transform into each other. This is critical for understanding how small particles behave when moving superfast and for phenomena like nuclear reactions. In reality, special relativity isn't just a fancy theory. It's something we use in everyday technologies like GPS. When GPS satellites send signals to your device, they are moving, and because of this motion, time behaves slightly differently for them. If we didn't account for this time dilation effect in our GPS calculations, your navigation would be inaccurate. Special relativity teaches us that time isn't the same for everyone and everywhere. It depends on how things are moving. This idea challenges our conventional understanding of space and time, suggesting that our usual perception of the universe is a bit off. According to the special theory of relativity, time isn't fixed, it's influenced by motion. Foundational ideas like the constancy of the speed of light and the relationship between energy and mass have been confirmed by numerous experiments. But there's more. Enter Einstein's general theory of relativity from 1915. This theory delves deeper into the relationship between gravity and the structure of the universe. It overturns the old idea that gravity is just a force that pulls things from a distance. Instead, it tells us that gravity happens because space and time are curved or warped. It's like saying, hey, gravity isn't a mysterious force. It's simply how things naturally move in the universe. According to Brian Cox's understanding, general relativity means thinking of the universe as a four-dimensional fabric, combining 3 dimensions of space and 1 of time. In this framework, massive objects like stars, planets, and even us shape how space and time are structured around them. This shaping is what we perceive as gravity. Imagine space-time as a large, stretchy sheet. When something heavy like Earth is placed on it, it creates a dent in the sheet. If you place something smaller like a ball near the Earth, it will roll toward this dent. This is similar to how objects behave due to gravity, not as a mysterious force, but as a response to the bending of space-time. Einstein's general theory of relativity doesn't just explain gravity in a new way. It opens the door to understanding the universe on a grander scale. For instance, it helps us grasp phenomena like black holes, which are regions where space-time is curved so intensely that not even light can escape. These enigmatic objects, predicted by Einstein's equations, challenge our perception of space, time, and even the nature of reality itself. One of the most fascinating implications of general relativity is its explanation of how time is affected by gravity. This concept, known as gravitational time dilation, suggests that time moves more slowly in stronger gravitational fields. Imagine 2 clocks, one on the surface of the Earth and another on a satellite orbiting far above. The clock closer to Earth, where gravity is stronger, ticks slightly more slowly than the one in orbit. This isn't just theoretical. It's a measurable effect that must be accounted for in technologies like GPS to maintain accuracy. Now, as scientists like Brian Cox expand on these ideas, new questions arise. Could our understanding of time and gravity be incomplete? Are there deeper, hidden layers of reality that we've only begun to uncover? Brian Cox's recent hypothesis challenges traditional views by suggesting that time and gravity might behave in ways even Einstein couldn't fully anticipate. Cox proposes that time may not be a single, uniform entity but rather something more complex and interconnected with the quantum fabric of the universe. He suggests that the interplay between quantum mechanics and relativity could reveal a new understanding of reality, one where time and gravity are intertwined in ways that defy our current perceptions. This line of thinking has profound implications for our understanding of the cosmos and our place within it. For example, Cox's hypothesis could shed light on the mysterious nature of dark matter and dark energy, which make up the majority of the universe but remain largely unexplained. Could the bending of space-time or the flow of time itself play a role in these phenomena? Additionally, it raises questions about the nature of black holes and the boundaries of the observable universe. What lies beyond the event horizon of a black hole? And could time itself cease to exist in these extreme conditions? Such ideas might sound like science fiction, but they are grounded in the quest to reconcile Einstein's theories with a strange and unpredictable world of quantum mechanics. This quest has led to the development of theories like string theory and loop quantum gravity, which attempt to unite the fundamental forces of nature into a single framework. While these theories remain unproven, they represent humanity's ongoing effort to understand the universe at its deepest level. As we journey further into the mysteries of time and gravity, one thing becomes clear: our understanding of reality is still evolving. The work of visionaries like Newton, Einstein, and now Brian Cox reminds us that science is a never-ending exploration, driven by curiosity and the desire to uncover the truth. So, as we ponder the vastness of the universe and the intricate dance of time and gravity, we are left with more questions than answers. What is the true nature of time? How does gravity shape our reality? And what secrets of the cosmos remain hidden, waiting to be revealed? These are the questions that will continue to inspire scientists, philosophers, and dreamers for generations to come. Relativity gives a strong clarification of how things move in our planetary system. For example, planets orbiting the Sun can be precisely understood using relativity, which explains the paths these planets take, including how Earth follows an oval-shaped orbit around the Sun. According to Brian, this idea differs from the old notion of gravity simply arranging things, which struggled to explain how planets move as they do. The groundbreaking idea is that space and time are bent like a flexible fabric, which aligns better with observations. An essential moment that demonstrated the accuracy of general relativity occurred during a solar eclipse in 1919. Sir Arthur Eddington led a team to observe how light from distant stars bent as it passed near the Sun. According to the theory, the Sun's mass would cause the starlight to bend slightly. During the eclipse, the observations matched Einstein's predictions, establishing the validity of the theory. Similarly, just as motion can change how we experience time according to special relativity, gravity also affects time. Where gravity is particularly strong, time moves more slowly compared to areas with weaker gravity. For instance, if you stood near a massive object like a black hole, your clock would tick more slowly than one positioned far away from this powerful mass. General relativity introduces black holes, regions where gravity is so intense that nothing, not even light, can escape. The boundary surrounding a black hole is called the event horizon, acting as a point of no return. Once something crosses this threshold, it is pulled into the black hole with no chance of escaping. Einstein's theory of general relativity has profound implications for how the universe is structured. Initially, Einstein added something called a cosmological constant to his equations because he believed the universe was static. However, when it was discovered that the universe is expanding, he referred to this as a significant mistake. The idea of an expanding universe, based on general relativity, is a critical component of the Big Bang theory, which explains how the universe began. Another significant concept from general relativity is gravitational waves, ripples in the fabric of spacetime caused by extremely massive objects moving rapidly, such as when black holes or neutron stars merge. In 2015, scientists at the Laser Interferometer Gravitational Wave Observatory, LIGO, directly detected gravitational waves, providing evidence for yet another aspect of Einstein's theory. Over time, scientists have conducted numerous experiments to verify general relativity, and each time it has proven to be correct, whether by observing planetary motion, the bending of starlight, or the detection of gravitational waves. While suggesting that gravity is not true might seem surprising, especially since we experience gravity daily, in the realm of physics, questioning established ideas is common. Scientists like Brian often challenge traditional theories, and in the case of gravity, some explore alternative explanations. One such idea is modified Newtonian dynamics, MOND, which proposes that gravity behaves differently at slow speeds, particularly in galaxies, without the need for dark matter. Instead of adding invisible matter, MOND suggests that gravity strengthens at low speeds. The debate about gravity also involves the mysterious concepts of dark matter and dark energy, introduced to explain certain phenomena in space. Critics argue that these aren't necessary and that alternative ideas could account for what we observe. Some scientists who disagree with Einstein's gravity theory explore possibilities such as unknown particles or forces that could refine or expand our understanding of gravity. It's important to emphasize that novel ideas in science are not dismissed. Instead, they are rigorously tested to determine if they make sense. For example, Einstein's concept of spacetime and the speed of light limiting time travel has been creatively studied alongside ideas like wormholes and shortcuts. Stephen Hawking's chronology protection conjecture suggests that traveling back in time is unlikely from a physics perspective. Ongoing studies aim to determine whether these new theories can explain phenomena like the strength of gravity in a way consistent with current knowledge. While alternative ideas have been explored, none have convincingly replaced the established principles of